We've been talking about trends on the periodic table, and that is a result of the structure of the periodic table. And the periodic table, as we know, built up well before the advent of modern chemistry, back in the alchemist days, where the elements were basically just being discovered and characterized, but reactions between them were being done, and they noticed that chemicals combined in certain ways, in certain proportions, certain relative masses. And from that, they were able to deduce what elements that had similar properties, elements likely to combine in certain proportions. And from that, the structure emerged, the columns of elements that had similar properties. And then we saw quantum mechanics describes perfectly that structure as well. So the trends come from that quantum mechanical structure, and we've been able to deduce them and look at them. Last time we stopped with this discussion of trends in ionization energies. So we see the ionization energies generally, you can see, generally increase as you go across. This is going 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. So you're going across a row of the periodic table. And as you go across a row of the periodic table, those ionization energies increase. It gets harder, more energy required, more endothermic to pull off an electron. And that jives with our understanding. We're adding electrons in the same principal quantum level, and the p electrons don't shield each other very well at all. So if you're just adding another p electron and another positive charge, you'd expect any given p electron to be more closely drawn to the extra charge on the nucleus. So harder to pull it off as you go across. And we'd expect the orbitals to be shrinking. Overall, everything is being drawn closer to the nucleus as I stay in principal quantum level 2, but I keep adding pluses to the nucleus. So we saw that dramatically when we looked at hydrogen and helium. We saw how the 1s, the principal quantum level 1 for hydrogen here, and then helium way down here, much lower in energy, much higher ionization energy, and smaller, contracting as that positive charge increased. And we looked at some of the little details where we thought that the 2s configuration, stable relative to adding and subtracting an electron, essentially, even though that's a little bit, it's stable relative to the nearby nuclei, to boron and lithium. And we were attributing that kind of in a hand-wavy way to the fact that that shell was closed. You filled up S, and that made that a more stable state relative to the elements next to it, and the half-filled 2p3 also exhibited that slightly more favorable, harder to ionize, lower in energy than the elements on the other side. So we can do a couple chem quizzes. Did we do this? No. Which has the smallest radius? Chlorine, argon, and potassium. So let's talk about that and see where we're at first thing this morning. So chlorine, argon, potassium. I think many of you can see the periodic table, I think, but we'll bring up the if you can put the output of this up here. There's essentially the trends in radius and ionization are there. So You understand radius, how it decreases across, increases going down. Talk about that, see what you think. Okay, let's see what you're thinking there after a relatively brief discussion. Argon, very popular, and I agree with the argons. I think you guys get the idea there. So the idea there is we can look at the electron configurations. There they are. Chlorine, argon, potassium. This jumps out, of course, immediately that's a whole principal quantum level higher than argon. So if you were going to compare argon, you'd say, well, argon's smaller than this one, lower radius than this. You've got a whole principal quantum level, you're going up one, and there's that 1s electron there. So you'd look then and say, well, what about between these two? And as you know, chlorine element 17, argon element 18, up there on the periodic table, that trend is smaller as you go across the row. You'd expect argon, it has that closed shell even that we said makes those ionization energies a little higher and those radii a little smaller. So you went with argon, and I agree. So how about lowest ionization energy among these three? So now we have two ions, same three elements, but the ions, chlorine minus, argon neutral, potassium plus one. So what happens here? And now I'm going to talk about ionization energy, but as you know, those are often the same trend because smaller is harder to ionize. So think about that and see what you think. Okay. Again, relatively brief discussion. The group I had pretty much nailed it. So let's see if that's consistent with the rest of the class. Yes, there's a lot of nailing it going on out there. Nailed it. I agree with the chlorines. Chlorine very popular. I agree. Why is that? These now are same number of electrons. Add one to chlorine, you go to that 2p6 or 3p6. Argon is in the 3p6, and take one away from potassium, and you're down to the 3p6. So there are three identical electron configurations, different elements. Remember, what determines the element is the number of protons in the nucleus and nothing else. All three of these species have the same electron configuration. That doesn't determine what element you are. And since they all are identical kind of quantum mechanically, they've all filled up in exactly the same way, same number of electrons. So the one with the biggest charge on the nucleus will be the hardest to ionize, and the one with the smallest charge on the nucleus will be the easiest to ionize. You're ionizing exactly the same electron. One of the 3p electrons will come off, and it's the 3p from the potassium, and the potassium has the highest charge on the nucleus, so the 3p's contracted in here, bigger charge, harder to pull off. And then the 3p from the argon and the 3p from the chlorine minus, all of them about increasing in size, and the biggest, the easiest to ionize, the hard, smallest charge on the nucleus, easiest to ionize. Great. So we're good with that, and those kind of questions you've seen them in your homework, and that's the kind of questions that'll appear on the exam. Just what is the general trend, and those are tractable problems. There's the conceptual stuff is there, but the conceptual stuff is relatively straightforward. More positive charge, same number of electrons. Harder to ionize the more positive charge you have. So here's one trend we'll talk about. We're going to define this term electronegativity, and this electronegativity is kind of going to have a trend that goes diagonally across the periodic table. So that's a little different than across our rows and down our columns. And we'll define the electronegativity in a kind of actually a hand wavy way. There are a lot of electronegativity scales. What we've been talking about so far, ionization energy and radius, those are things that you can measure, and it's objective difference between the atoms. Electronegativity is slightly different in it refers to the relative in a bond, relatively in a bond, who is more likely to draw the electrons towards the nucleus. So when you have a bond, you have two nuclei competing for the electrons. And the one that's a little better competitor is the more electronegative. And you have to do this by measuring the polarity, the unevenness of the bond. And you measure that unevenness. This Linus Pauling, we're going to use the Pauling scale. Did he get a Nobel Prize for that? Anybody know? I think he did. I forget. I don't think this was the Nobel Prize work. I think this was just some other stuff that he did. Somebody Google that. And here we have these values. So sodium, over here on the periodic table, small electronegativity. Chlorine, high electronegativity. And if you're down here in the potassiums, rubidiums, franciums, lower and lower and lower electronegativity, and higher electronegativity here. And we're using the negative sign for higher electronegativity. So these are positive, and these are electronegative elements. As we go across, we know N is increasing there, the effective nuclear charge increasing as we go across. That effective nuclear charge increasing is what's causing those contractions in radii and those increases in ionization energies. And these are going to lead to how the elements bond together. So a small high charge nucleus with a large low charge nucleus, you would expect electrons to favor that high charge nucleus. The trend, though, is positive to negative. So we'll define it in terms of polarity and bond strength. So now we're going to talk about bonds. This is our first real discussion of bonds. And we're going to classify them by the difference in electronegativity. So these numbers you'll be able to look up. And in general, we don't, I can't think of an exam question we would ask where the actual number is important. You'll just look at the general trend. These guys are electronegative. These guys are electropositive. So if there's a big difference, and now we're giving it a numerical value, bigger than 2 on this Pauling scale, that means that refers to a very polar bond. If the electronegativity is different, very different, then one of the elements is more electronegative, draws the electron cloud. They're both competing for electrons, but the electron cloud favors the more electronegative element. The bigger that difference, the bigger that polarity of the bond. And when I say polarity, I just mean there's a plus and minus separation. So it's polar because the polarity refers to plus minus separation. There's a direction in space you can define because of the separation of charge. In sodium chloride, the chlorine is so much more electronegative that the electrons are actually spending all of their time, almost, the extra electron around chlorine. So chlorine has essentially a negative charge, leaving sodium with a positive charge. So that is a giant difference in polarity, a whole negative charge here and a whole positive charge here. Those bonds are called ionic bonds, and they're the strongest bonds because that polarity. So you can come together and the electron clouds can overlap, and that's great. But if one of you goes to positive and one of you goes to negative, that's going to hold you together too. So these are very strong bonds. So higher polarity, higher bond strength. Take nothing else home from Chem 1. Take home the fact the more polar, the more you separate the electrons, the stronger that bond is. And you can appreciate that because that polarity itself starts to hold the molecule together. You have to overcome that when you pull them apart. So partially ionic. So now we're gonna, we're gonna introduce some notation here. This little symbol, Greek lowercase d, delta, with the charge. So here it's a full +1 -1 charge separation. When we say partial charge, we use this little partial d sign. So this is not full +1 and full -1, but the electrons do favor the chlorine. So we say there's a partial charge, negative charge on the chlorine, and that results with a partial positive charge on the hydrogen. So those are what we'll call polar covalent or partially ionic. And if they share equally, of course, if it's homonuclear, then that's a perfectly equal sharing, and that's not a polar bond at all. So no polarity to help with the bond strength. So low differences in electronegativity, you get polar covalent bond. The perfect example is homonuclear, but there are carbon-hydrogen bonds are not very polar because their electronegativities are about the same. So they're nearly perfectly covalent. So how does that, this one, so we had two straightforward ones to start. This one's going to require some head scratching. So let's look at hydrogen gas reacting with either iodine, I2, bromine, Br2, or chlorine, Cl2. So those gases to form the hydrogen iodide, hydrogen bromide, or hydrogen chloride. So those are all exothermic. But can you predict what might be the most exothermic among them based on the fact that you know what element is here and you know electronegativity increases as you go up to that corner of the periodic table, high electronegativity up there in the upper right? Does that give you some predictive power about what's happening there? So let's talk about that one. That's going to require more discussion and head scratching, I think. So thinking caps on. And if I could have the output of the lectern up here, so we see that trend in electronegativity and that discussion of polar bonds. And I'll start the chem quiz. You guys can start the discussion. Are we unable? Oh, there we go. We're shifting up there. So you have your electronegativity scale there. Go ahead. Let's talk about that. Uh, Okay, let's see what we're thinking. And this one we'll probably have to talk through. Let's see what you're thinking. Oh, well, maybe not. There's a lot of help in the crowd. That's suspicious. So now I'm interested. A lot of you voted A, chlorine, and be honest. Why is that? Could you hear me over there kind of going through it, or were your GSIs very good with helping you out? Oh, it's already been in the homework, so you might have done the homework. Forgot about that. So normally, if I give this chem quiz and it's not in the homework, nobody has any idea what's going on. So you guys can approach it in one way. I've seen it before. I can say the same answer. That doesn't mean you understand it, because if you do it in the homework, you can see it tells you what the correct answer is. So that memory of what it is helped. In fact, we should probably purge those chem quizzes from the homework. I don't expect people to be working that far ahead. I rely on your inherent lag between what we're saying and how far you are ahead in the homework. But right next to an exam, I'm glad you're very current and working on the latest stuff. So yes, that's true. 80% of you got it right. Can 80% of you explain why that's the case? Because remember, even though that's a homework question and it could appear then on the exam, I'm probably gonna doctor it a little bit, so the answer won't be the same element, and you'll have to understand the reasoning to get the answer right. So getting the answer right, especially on the homework, is not is a indication that you did the homework, but is it an indication that you understand the argument? So, and I talked to some very smart people in the audience, and we had to work through it, and the argument wasn't clear to them. So why is this the case? Why is chlorine the best answer there? And this, the beauty of this chem quiz, and the reason it's nice to have it here, is you could work it out with a lot of just reasoning, but the reasoning is a stretch for where you are in chemistry right now, your overall chemical career. You should be looking at these things, and especially when it's a picture, because you know I love to draw pictures. Why did I draw it in a picture instead of H2 plus X2 goes to 2HX? I could have written it like that, right? But instead I drew the picture, emphasizing these bonds and these bonds, okay? So why is that exothermic? That's exothermic. How would this reaction proceed? Well, in some sense, you have to break those two bonds and make those two bonds. So that's a first approximation to how that reaction might go. So the first step, the breaking, that is endothermic. And we know that if you take nothing else home from Chem 1, breaking a bond is always exothermic. There's so few always in life. Breaking a bond is always exothermic. I'm already at the making. The making is always exothermic. So I always have to put energy in to break. And then the converse must be true, that if it took energy to break, any making bond must release energy, must be exothermic. Okay? So the reason overall this is exothermic is the breaking energy must be less in magnitude than the making energy. So the difference between the two is still net release of energy. So that part, walking through those steps, is something that you kind of had to do to figure out what was going on here. And then you say, well, you take another conceptual step. Okay, so if I'm making bonds and I'm releasing energy, which bond releases the most energy? Which goes farthest down in energy? And the one that goes the farthest down, the biggest release of energy when the bonds is formed, is the one that'll be the most exothermic. And then you have to go back to what we said today and make that one more conceptual step. Say, well, the strongest bond is the most polar bond, and strongest bond, it's reasonable to make the connection. We haven't said that, but the strongest bond should release the most energy when it's formed. So those three conceptual steps are pretty big conceptual steps, and you have all the machinery to do them, but still some of them were kind of a stretch and would take a lot of thought for you to work through that. But that's the argument you made. So the end result is, which bond is most polar, which bond is most strong? The most polar is the biggest difference in electronegativity, and it's H for all of them. So it's which one of these, iodine, bromine, or chlorine, is the most electronegative, which would make that the most polar bond. So you go for the highest electronegativity, most polar bond, and the trend in electronegativity up in that right-hand corner are the most electronegative. Chlorine is bigger than bromine, is bigger than iodine. So that's HCl releases the most energy when it's formed. That's the most exothermic. Most polar, most exothermic. So following all those arguments, you've taken in stuff from the entire class almost. All that thermodynamics, all that pulling and breaking. What made that one conceptually challenging is you had to push forward kind of in concept. You really had to apply the concept in a very thoughtful way. Okay, so here we are on our roadmap to the course. I guess it's appropriate to stop and pause. Where are we on a roadmap to the course? Remember way back, first day, we said our goal in Chem 1 is to understand pretty much everything on this picture. And we've been ticking off the check boxes as we go. So we started with this part, reactants, products, the difference in energy, thermodynamics, when the reaction goes, is energy absorbed or released? And free energy was the important one we got to. If free energy decreases from the standard state, that's what we call a spontaneous natural process. And you could imagine this being free energy plotted here. But we plotted everything. We plotted enthalpy on that axis. We plotted entropy on that axis, free energy on that axis. And in every case, you should be able to arrange the products and reactants in enthalpy, in entropy, in free energy. You should be able to do all those things. And free energy, you should be able to arrange the products at different temperatures. The enthalpy and the entropy arrangement stays the same as the temperature changes. But the free energy can change, as we know. So we can do that. We talked about kind of the dull stuff, the stoichiometry, the relative masses that allowed us to look at equations, balance the mass, balance the number of atoms. We understood that this 9 here represents either 9 oxygen atoms for every 1 glucose atom, or 9 moles per mole, or 9 relative masses of O2 reacts with 1 relative mass of glucose. So we did that. We've done the order, energy, and heat, talked about thermodynamics, and bulk matter. We looked at changes in phase and the differences between bulk matter, especially the condensed versus the gas phases. We talked a lot about the gas phase. We understand a lot about the gas phase, the energy involved with ideal gases, how that goes directly with the temperature, the pressure volume relationship, and the condensation or vaporizations themselves. We talked about entropy for that and enthalpy for that. And we're able to plot free energies for condensations, phase changes, and we looked at the phase space. And now we're here. We've come to the quantum mechanical descriptions of the particles themselves. So, boy, we're getting near the end, aren't we? We're understanding the quantum mechanical structure of the particles themselves, which allows us to talk about what we're talking about today, the bonding of the particles together. So we understand the atomic structure, the periodic table, and we can start to look at the structure of these molecules and oxygen, hydrogen, quantum mechanical bonding. How strong are those relative bonds? Why is water not a linear molecule? Why isn't it hydrogen, oxygen, hydrogen in a line? Why is it bent? Those are the things that are the topics of the next couple of days. Okay. Oh, and we talked about that part. The kinetics, the high road pathway that sometimes prevents, even though this is lower in free energy and the universe would favor that state, it might be impossible to get there if this activation energy is too high. So sometimes things stay in a not so thermodynamically stable state. We kind of talked about that with oatmeal yesterday. We said the most stable form of the oatmeal flake is the oatmeal flake glued to the side of the bowl, relative to the oatmeal flake in the cooked oatmeal, relative to the oatmeal flake in the bag of oatmeal. So the bag of oatmeal would stay the flaky bag of oatmeal forever unless something happened to get it over that activation barrier, heat it up, cook it on your stove, put water in, and then it's gonna end up in that stuck to the bowl state sometime later on. If the universe lasts long enough, all the oatmeal will be stuck to all the bowls in the It's called the oatmeal death of the universe. Oh, goodness. I'm glad I amuse myself, even if you are not amused. I have to have some fun too. So we had catalysis to that discussion. Here's the animation of the thermodynamic part of the discussion. So now we're going to move on, as we said, and talk about those bonds, the structure of the molecules involved. And here I've put together parts of the periodic table. So the Hahi, Libby, Basi, Nafni, Namgyal, Subs, Clark, part of it that we can do phonetically if we have to, and we don't have to. And I've drawn them with their, what we call valence electrons, their outermost shell electrons as dots. So 1s1, 1s2. And here it's a 2s1, 2s2 on beryllium. Then 2s2, 2p1, 2s2, 2p2, 2p3, 2p4, 2p5, 2p6, until there's 8 electrons, the 2s's and the 6 p's here at the end of the periodic table, the last column of the periodic table. So just arrangement of dots and the electrons as dots. And in the end, we hate electrons as dots. Well, you might not hate electrons as dots. If you're an organic chemist, electrons as dot is your favorite thing. but then you're just a cook, so it's all you need. If you're a physical chemist, the dots bother you. Number one, electron is not there, for damn sure. And it doesn't behave like a point particle. And this accounting is very hand-wavy, but it's hand-wavy accounting, but it's very good. And it is the basis for developing the periodic table in the first place. Before we knew quantum mechanics, oxygen was stacked on top of sulfur because of that. They both have that same outer shell of electrons. We call those the valence electrons. The outermost principal quantum level is usually what we're describing there. So here, the outermost principal quantum level is the S. There, it's the S and P together. And we talk about valence electrons, the outer shell electrons. They're the electrons that do the chemistry. The electrons deeper in the core are not available. They're not outside. They're not available to do the chemistry. So these are the ones involved in the bonding. So even though aluminum has many more electrons than boron, we're still going to talk about aluminum as a 3-valence electron and a boron as a 3-valence electron system, because our bonding is just among the valence electrons. Okay, and we talked about this concept, full shell. We've completed the S and P orbitals, filled them all up, and we've got to neon and argon, and we saw how that made them. It gave them those high ionization energies relative to the elements around them. And this idea that that's 8 electrons, 8 valence electrons, leads to this octet idea. 8 electrons is somehow a stable, a favored number of electrons in the valence shell. And we know why that's favored now quantum mechanically, because that's filling all your S's and P's. And that leads to this lower energy configuration. That lower energy configuration relative to those around it is referred to as stable configuration. Lower energy configuration is the octet. So the octet is a common thing. And then Gilbert Lewis, for whom Lewis Hall is named here. Everyone in the country, of course, studies Lewis structures, but you guys are right next to the building named after him. So he developed the idea that, well, if 8 seems to be a favored state in the atoms, does that relate to how bonding occurs, how molecules form? Is there a tendency to lower your energy by attaining 8 valence electrons? That was his idea. And in general, it's true. Although we're gonna slide helium over there into the full shell. In helium's case, the full shell is a duet, just a pair. And that's why you see helium slid over in the periodic table over to that full shell. It behaves more like neon and argon because of its closed valence shell. So that idea, should I get 2 or 8 electrons as a molecule? It leads to that lower energy state when I'm an atom. Should we apply that to a molecule? And again, it is not a bad approximation. It does have predictive power. It's not correct by any means quantum mechanically, but it has predictive power and allows you to do a lot of things very quickly, predict a lot of things about bonds. So we're going to use it a lot. So we talked about this ionic bonding already, this very polar interaction. And ionic bonding, indeed, it's so polar, one element is so much more electronegative than the other, that it's a complete electron transfer. Electron goes from the electropositive to the electronegative element. The electropositive element becomes positively charged. The electronegative element becomes negatively charged. And then it's that full Coulombic plus minus attraction, which is much stronger than a covalent bond, holding that together. And these are the salts like sodium chloride that the bonding interaction is very strong due to this. And then the fact that you stack them up all in a lattice and have the plus minus lattice energy holding the solid together. We're not going to talk too much about that. So here's the dots picture of that. Here's lithium, fluorine, electropositive, electronegative. Fluorine, the more electronegative element. The electron transfers to the fluorine, leaving lithium, the positive charged ion, and fluorine, the negatively charged ion. And that is an ionic bond. Those two then stick together close in space due to the plus minus Coulombic attraction. And sodium chloride, the same thing. And you would expect elements in row 1 or column 1 of the periodic table, and over there in column 7 of the periodic table, electronegative. You have this idea 8 valence electrons is good. Closed shells are good. Closed outer shell. Fluorine and chlorine, it's obvious from the picture. Those have attained 8. Lithium and sodium lost 1 electron, but that 1 electron was an S electron. So below that is that closed shell sp. So they actually get to the closed shell sp 8 valence electrons by removing that S that was the valence electron. So the argument holds quantum mechanically for lithium and sodium in that state as well. And maybe magnesium chloride, here magnesium takes 1 electron from each of 2 chlorines. The chlorine, 2 chlorines take the 2 valence electrons. Magnesium right next to sodium up there, element 12, has 2 S electrons, and 2 chlorines can take those. Each chlorine would be a negative. The magnesium then would be +2, and the 2 chlorines each -1, and that would form that ionic solid magnesium chloride. So here's our relating this back to what we talked about yesterday. So in some sense, that transfer of electron from one to the other involves an ionization, because you're pulling electron off one and going to the other. Getting a little feedback on the mic. Goes from one to the other. So that involved ionizing this one, and the electron ended up on the other, so that involved the electron affinity of the other one. So there's a sense of balancing electronegativities and ionization, and electron affinities and ionization energies involved there. So we could look at what happens. We'd notice that that's not the whole story right away. So if you're going to form sodium chloride, you'd say, well, sodium's going to give up the electron. I have to ionize that. And then chlorine's going to accept it. So that's the electron affinity for chlorine. So here's the ionization energy of the sodium. Oh, put in 496 kilojoules to pull that electron off sodium, put it on chlorine, release 349 kilojoules per mole. So is that exothermic or endothermic overall? It's endo. You had to put more in to ionize than you got out from the electron affinity. So that's not the whole story. The whole story includes, well, once you've done that, then you have all that energy of them attracted to each other. And that going down in energy is also exothermic. Plus minus attraction helps you. And then with sodium chloride, a tremendous amount of energy because it's in a solid lattice structure that's very, very, very stable. So we can understand a little bit in the gas phase, maybe those numbers would be exactly right. But the solid, the bond forming, makes it overall exothermic. Here are those lattices. Here's some sodium chloride crystals. Here's an X-ray micrograph. So you're looking at incredibly tiny crystals of salt. But you may know salt forms square crystals anyway. The salt particles coming out of your salt shakers are squares. You can see that with just a regular magnifying glass. This is on the micro scale. That sodium chloride arranged in that compact array, very stable. And here's this just an interesting result. Because they arrange in the square arrays, some square arrays are more favorable than others. So if you look at all your possible little cube sizes, some of the cubes are more favored than the other cubes. And this is just saying of all the masses, you get lots of these kind of cubes and these kind of cubes. So they are good size cubes. So that closed cube structure, when I get to 364 particles, that closed cube structure is a particularly energetically favored one. And so there's kind of a quantization of salt crystals, salt chunks. Kind of interesting aspect of this whole thing. Not part of the course material really, but since it's a quantization, I thought I would show it to you. Quantization in sizes of particles, favored particle size in sodium chloride. Okay, so let's apply that. Which element forms a bromide, so reacts with bromine gas, Br2, that's 80% bromine by mass? So here are the relative masses. Calcium, potassium, neon are the options. Which forms a bromide that's 80% bromine by mass? So think about that. Talk about that among yourselves. Start the thingamabobber and we'll take a vote. there's the more helpful information for this chem quiz. Let's see what you're thinking. Deprived of that helpful information. Well, thanks for giving it to us now. It's funny, back in the old days. So the helpful information. You notice how Pimentel has 8 chalkboards available, more or less? There are chalkboards underneath these chalkboards too. So you can, once you've written something here, you can push that up and write something here and keep that up there. So you have chunks of information available, 8 chalkboards available to you. And you may notice that by and large, every little lecture has 4 PowerPoint slides, those groups of 4 with information, and about 4 chem quizzes. And that comes from the fact that we would get 4 information boards and 4 chem quiz boards. And then we would lift it up and we would see the solution to the chem quiz boards. But you would have all the information all the time in front of you because we didn't write, even then we didn't write during the class, came in early, and basically we would draw this on the board. So these PowerPoint slides, a lot of them came from taking pictures of the chalkboards and then transferring them into PowerPoint slides. And we end up with the same chunks of information. Anyway, historical footnote. Everybody's, or a lot of us have decided C, or calcium, is the right answer, and I agree with you. Here's the conceptual steps you might have taken. You have to make a neon bromide, a calcium bromide, or a potassium bromide. Will a neon bromide form? Not likely. The idea is bromine accepting an electron. It's the more electronegative, perhaps. Will it accept an electron from neon? Well, maybe, but neon already has a closed octet. It already has an octet. Neon is happy the way it is in terms of dot structures. That is a stable closed shell. And as you know, we looked at neon and said, has a high ionization energy and a low electron affinity. It doesn't want to take one or leave one. Hard to take it, and you don't get much energy back if you add one. So that's just not a likely thing to happen. For potassium, then yes, potassium's got that dangling electron out there in an s orbital. Beneath that is a closed shell, 8 electrons, 2s and 6p electrons. So removing that is good, and it helps bromine because that gives bromine the octet, and then the plus and minus interaction, and that's your salt, your ionic bond, your molecule. Here, reacting with calcium, now calcium has 2 s electrons, 2 outer shell valence electrons to give up, so 2 bromines could react, and you would get calcium plus 2 and 2 Br minuses. Overall, that's still 0 charge. You haven't added or subtracted any electrons or protons from the universe. You just keep the same amount, shuffle them around, so the overall charge has to be 0 when you form your ionic bonds. And you see calcium reacting with 2 bromines, and then you just have to see, well, which one of those between KBr and CaBr2 is 80% bromine. So potassium bromide, that's 40 and 80, so that's 120. 80 of it is bromine. Excuse me. Yes, calcium bromide. Potassium bromide, 40 and 80. And then calcium bromide, very similar molar mass, very similar relative mass. They're just off by 1. So about the same. and 2 bromines. And that is the higher percentage mass. And you can do that calculation. 160 here and 40 there. So bromine is 160 out of the 200-ish. That's about 75%, 80% bromine by mass. Okay. Now, oh my gosh, another one. This is another great chem quiz for the day before the last lecture before the exam, because now we're going to talk about, this is similar to that hydrogen bromide that we the 3HX versus XX and HH. This is a similar kind of idea. You think about it like this. There's the atoms, say the chloride and lithium. So lithium and chlorine are coming together in the gas phase, a chlorine atom and a lithium atom. And at some point, that electron transfer is going to happen. Lithium electron is going to end up, that little arrow we've been drawing. That little arrow thing has to happen at some point. The question is, how close do you have to get for that to happen? And maybe this is in the homework too, so you'll all just say, oh, I'll just give you the homework answer. But why is that? Can I rationalize which of these will the electron be most willing to jump? Will it jump earliest, the biggest R? Here they come together, and that electron, this electron over here on the sodium or the potassium or the lithium is wanting to jump over there. And at what point does it say, yes, I'm going to jump over there? So think about that for a minute among yourselves, discuss that, and we'll take a vote on that. So I'll give you a hint as you're discussing this. Once that electron jumps from here to here, then you have a plus thing and a minus thing. And that's where the potential energy jumps into the equation. Okay, first you have to overcome the fact that that happens, but then, bam, you get something stable, and it's more stable, lower energy, the closer they are together. Okay, add that to your discussion. Okay, this one requires a lot of thought, or having looked at the homework. I don't know if this one's in the homework. So let's see what you're thinking. Thank you for switching. Up there, we're thinking potassium is the one to go with. Let's talk through the idea. Here's part of the idea. Look at this. We're going back to the first week of class where we said plus minus interaction. The closer you are together, the more energy you get out. Lower energy, more exothermic, more stable. Energy is coming out as you go down. So that's a release in energy as I come closer together. What are you going to use that release in energy for? Well, you had to pull an electron off. That takes energy. So you're doing that electron transfer, that takes some energy. You need to get that back from the plus minus coming together. So the harder it is to pull those off, the closer I have to get together before it's worth pulling it off, before it'll come off. So I have to balance those two things. So the easier it is to pull off, I don't have to get quite so close together. Well, what's the easiest to pull off? Lithium, sodium, potassium. I didn't give you any numbers, but that periodic trend. Lithium, sodium, potassium, ionization energies, that's the one we did. We dropped the metals in the liquid there, and we said, oh, potassium's the easiest to ionize. It released the most energy when that other reaction occurred. Same thing here, easiest to ionize. I don't have to be quite as close together for them to happen. So this is going to go as the trend in ionization energy. So the low ionization energy, that transfer can happen at a relatively large distance. The high ionization energy, that transfer happens at a smaller distance is required to balance the fact that that took energy to transfer the electron. Okay? So that's what we were looking for. Forget what the question was, but if the answer is potassium, it must be the greatest R is what we asked for in that quiz. All right, fantastic. We're going to stop a little early today because organic chemistry has midterms and they do it in person in the class. So we'll give them a little extra time to file in here. So I'll just go through this last bit. We're going to talk about ionic bonding, where the electron is transferred. Another way to complete your octet would be to share. Oh, I like that better. So you can imagine two chlorines sharing these two electrons, this pair of electrons between them. So this chlorine can count it towards its 8, and this chlorine can count it towards its 8, and they both can count 8 by sharing the pair. And that's a covalent bond. We call it covalent because there's no charge separation. Ionic bonding is named for the fact that those are ions, plus minus charge things. There's no plus minus charge things here. These are perfectly covalent, these two. The electronegativities are the same. There's not even a little charge separation, not even the partial ionic separation, because they're homonuclear. But of course, this happens, it doesn't have to be homonuclear. Here it is, hydrogen and chlorine sharing that pair of electrons. So hydrogen has its 2, that's a full shell for hydrogen. It looks like a helium, 2 s electrons is going to close that shell, and chlorine getting the 8. And then we replace that pair of electrons with a little line saying that's a bond between those two. So there's our first bond in the class, really. The ionic interaction is exactly that. It's Coulombic, plus attracting minus. The electron moved from here to here. There's no sharing, there's no bonding interaction. This is an overlap of atomic orbitals where we can do the quantum mechanical description of that. And you probably already know what we're going to do. We're going to say, well, your electron is there in an orbital, and it has a phase. It's in a standing wave. That electron's in a standing wave. And hydrogen, your electron is a standing wave. Let's come together, but let's come together so that what happens? There's constructive interference between the two standing waves. Woohoo! That says, oh my God, the electrons, high probability of finding electrons there. And I can talk about waves forming bonds rather than this rinky-dink dots forming bonds. But the dots work. So, and I won't say that too loud, the people coming in love the dots. They're the organic chemists. We sometimes, I don't know if Pete can hear me, he's back there. We sometimes call the organic chemists electron pushers because they just push the dots around in their little structures to see what the bonding is going to be. And well, which is great because that's simple. And then we're sitting there as physical chemists with our supercomputer trying to figure out, oh, that electron just went there. But we have to do all those orbitals and do the math and add them together and see if there's constructive or destructive interference. It's a little bit of a chore, but it's the right answer when we get there. Okay, so here is a summary of the octet rule. Here are some compounds obeying the octet rule. Oxygen with its 6 valence electrons, so 12 electrons total, 2, 4, 6, 8, 10, 12. Those are the total valence electrons for 2 oxygens. And if you share them like this, remember each line is a pair now. So this oxygen can count 2, 4, 6, 8. And this oxygen can count 2, 4, 6, 8. Who do we appreciate? Nitrogen, same thing, 5 valence electrons, 10 total then. 2, 4, 6, 8, 10. How do you share 10 so that each has 8? Each think they have 8? Well, you share 2, 4, 6 of them, and you have 2 that each nitrogen has to itself. And carbon monoxide, look at that, isoelectronic. That has 10 valence electrons. Carbon 4, oxygen 6 valence electrons, also 10. And look at that, it does the same thing. Shares the same way nitrogen does. Here's one hydrogen electron, a hydrogen electron coming in here, a hydrogen electron here, and a hydrogen electron here to complete the 4 valence electrons of carbon. 1, 2, 3, 4 hydrogens, bring that up to 8, and each hydrogen can count 2 if I share like that. But there are exceptions. Here's boron trifluoride. Here, all the fluorines are happy. They have 8, 2, 4, 6, 8. But the boron is electron deficient. It has only 6 around it. But that still forms. That's still a stable compound. So it's not always true. And you can also expand the octet beyond 8 electrons. So this xenon, 2, 4, 6. Oh, and be careful here. I've drawn a line and the pair. This is just the pair. This isn't 4 electrons. So lone pair, lone pair. So xenon counts 2, 4, 6, 8, 10, 12. It counts all those electrons, just gobs of electrons around that. Sulfur counts 2, 4, 6, 8, 10, 12. And the fluorines, I stopped drawing the other 6. That just gets tedious. And you're allowed to do that. You don't have to say, we understand if fluorine does this, its 6 valence electrons are still there, completing the octet.